testing. Okay. Can everybody hear me? Okay, so we get going. Okay, so at the end of last lecture, we were talking about breadth first search, which for our purposes is a better searching algorithm than depth first search was. But we saw that it found better paths than depth first search. They weren't quite so crazy, but they still weren't the shortest travel time in many circumstances. So I gave you this little example of a graph, and breadth first search will start searching at the source, and then it'll find I can get here, and then here, and here, and it'll take this path, which is not the shortest one, okay? There's a shorter path that goes the other way, but standard breadth first search doesn't find it. And it doesn't find it because it marks every node as visited once it finds it once. So it starts at the source, and the next nodes it'll look at will be this one and this one. It'll mark them as visited. Then it'll look at this one, then it'll look at this one. And the first time it reached node 1, it reached it through this path, it marked it as visited, that's the one it'll use. But if you add up that travel time, it's 24 seconds, and there is actually a shorter path if you go the other way. Okay, so breadth first search won't find it. Now we can tweak breadth first search. We can make something that's a little beyond breadth first search, which I call re-expansion, being willing to look at the same node, the same intersection more than once, and that can actually fix this problem. So let's see how that works. Basically, the technique is instead of just marking a node as visited the first time we see it, we actually record what is the best travel time I've ever seen to this node. And we only update its data if we found a new shortest time. This is a bit more robust. It will allow us to find the best paths with this new tweak on breadth first search. Okay, so let me show you how that works. So this is basically still the same algorithm. I've just changed one thing. So just like breadth first search, we start off by taking our source and we put it in our wavefront, our to-do list of what to do next. So that's node 0. I'm going to start there. I look at my wavefront, take whatever's at the front of it out, so that's node 0. And node 0 is not my destination, so what I do is I look at the edges coming out of it, there are 2 of them, and I take the nodes on the other side and I put them in my wavefront. Okay, so now I've got nodes 1 and 2 in my wavefront. Remember, there's this big while loop that I'm going to show you again in a minute, but it basically says take the next thing out of the wavefront. So that's going to be this, node 1. Okay, so we're going to take node 1 out of the wavefront. Now we're looking at it, and we've got to keep track of what the best path is we've ever seen to a node. So we look at node 1. We've initialized what is your best time that I've ever had to reach you to some big number. So I'll see, I've now reached you with a travel time of 15 seconds. Let's update you. Best time I've ever seen to reach you is 15 seconds. And remember, we're also, so that we can find our way back later, we can find the path, we're storing this reaching edge. So I'm storing 2 things. I reached you through edge A, and when I reached you, the travel time was 15 seconds. Okay, so I still haven't reached my destination, so I throw away that node 1. Node 1 can reach node 3, so I put that in my wavefront. So now I've got 2 and 3 in my wavefront. Big while loop goes back, takes the next thing out of the wavefront, which is node 2. I record that I reached it through edge B, and I record that the best travel time I've ever seen to get here is 5 seconds. Okay, still not at my destination, so I basically say, okay, well, throw into the wavefront what I can reach, which is node 1, right? I can follow this edge to get to node 1. And so now I've got node 3 and node 1 in my wavefront. Take out the next node, so that's node 3. I'll go look at this. I'll update how I got here. So I got here through edge D, and my best travel time is 21 seconds. Not at my destination, so I say, what can I reach? Well, I can reach node 4 through my outgoing edges, so put that in the wavefront. Now the thing at the front of my wavefront is node 1. Okay, and a node 1 I've already been to. Okay, but I'm going to take it out of the wavefront again. And with classic breadth-first search, I would just immediately throw it away. I'd say I've already visited it, don't need to do anything. But I'm instead using this different condition. I'm going to say take node 1 out, and let's look at what travel time I have. And I stored the travel time. So I haven't shown it, but I'm storing the travel time in the wavefront as well. So I've reached node 1 again. I took it out of my wavefront, but this time I reached it through a different path. I came through node C, or edge C, and my travel time was better. It was 10 seconds. Okay, so it used to be a 15-second travel time. I update it to 10. And I update how I got here to say I got here through edge C. Okay, so the only difference versus classic breadth-first search is I'm not using a visited flag. I'm recording what's my best travel time ever to each node. When I pull something off the wavefront, I check, did I find a better way to this node? If I did, I update its best travel time ever, and I process it, right? I check, is it my destination? If it isn't, I go look at all of the outgoing edges and put the nodes on the other side in the wavefront. Okay, when I do that, if I keep running this algorithm for a while, it basically is eventually going to pull the destination, node 4, off of the wavefront. Okay, but I'm not going to end the algorithm yet. I keep going for a while because maybe there's an even better path, and eventually I pull node 4 off the wavefront again, and I've found the shortest path to it. Okay, so it's kind of a tweak on breadth-first search where we just use this different check at a node of should I do anything with you. And this updated algorithm does actually find the shortest path, and it'll always find the shortest path. So we fixed it. Okay, so I went through that pretty quickly. If anyone has any questions, put up your hand. Otherwise, I'll just show you the code, which is pretty close to what we had last week. We just tweaked it a little bit. Okay, so let's look at what have I done to the code. So breadth-first search, we already had this wavefront, and I created this data structure wave element that had two things in it, ID of the node and the ID of the edge that I used to reach it. I need to add a little bit more to it. I'm going to add, what's the travel time? What's the total time to get to this node that I just stuck in the wavefront? I need to keep track of this now because whenever I pull things off the wavefront, I'm going to do this check. Did I find a better path to this node? So to do that, I need to store this travel time. For convenience, I've also made a little constructor here. Just takes 3 numbers and sets up my wave element. Okay, so that's one of the changes I had to make. I had to store a little bit more information in my wavefront. And I also have to store a bit more information or a bit different information in my node. And remember, my node data structure is, well, this is information that I'm going to store for every single node, every single intersection in my graph. So I've already been storing what is the ID of the edge that I used to reach you. But I'm also going to store what is the best travel time that I've ever seen to you. Okay, so I got to store this. Sometimes this confuses students, but I've got to store this time in 2 places. In the wavefront, because the wavefront is my to-do list. These are the things that I should look at next. And in this node data structure, which is like my done list. This is like the best stuff I've ever found to every node in the graph. You need both those data structures for this algorithm to work. Okay, what does the code look like? It's very, very similar to the like the classic normal breadth-first search that we did before. So basically, our iteration is a little longer now. We don't iterate until we find the destination, because we might not find the best path to the destination the first time we see it. So we actually keep searching as long as the wavefront might have a better solution. Okay, so as long as the travel time of any node in the wavefront is less than the best travel time we found to our destination, we keep searching. And then we do mostly what I showed before. Basically, we take from the front of our wavefront, we're using a list for that right now to make a queue. So from the front of the wavefront, we take the next item, the next node to look at. And in bold is what we've changed from classic breadth-first search. We check, is the travel time of this to-do item, this node reached through some path that I just took off the wavefront, is that smaller than the best travel time I found before to this node? If it is, I want to update its state, okay? I want to say, I've reached this node through whatever edge I used and put on the wavefront, and the best time I've ever seen to get to this node is whatever travel time I recorded on the wavefront, okay? The wavefront was a possible way to get to this node. I check again, am I at my destination? And if I am, I record that I've found my destination. If I'm not at my destination, I gotta keep going. So I go through all of the outgoing edges from the node I'm at. And for each one of them, I figure out, well, what node, what intersection is on the other side of this edge or street segment. And then basically I say, put it on the wavefront. Wavefront's my to-do list of what to look at next. So I put the node ID of this intersection that I could reach with an edge. I put on the ID of the edge, because remember I need to keep track of that so that I can backtrack and find what was my path when I get there. And then I also have to store, well, what is the travel time to that node that I'm putting on the wavefront? And it's basically, what is my travel time to where I am right now, my current node, and then add in whatever the travel time is to go down a street segment, maybe have a turn, and get to the intersections on the other side of that street segment. So that's what I put into my wavefront, and that's it. I just keep going through this while loop until I break out, which means I know there are no better paths to the destination, and then I return whether or not I found a path. And at that point, I can invoke the exact routine that I showed you at the end of last lecture, which will do the trace back. We'll, from the destination, trace back through these edges we've recorded and reconstruct the path. Okay, so if you were here on Thursday, this should look really familiar, okay? Because this algorithm is pretty close to breadth-first search. It just has these little changes of we can look at a node more than once because we're not using a visited flag anymore. So one of the things I want to think about is, so that algorithm will work, okay? It will find the shortest travel path. I want to think about how fast it was. We looked at depth-first search and we found it was fast. Depth-first search was order n, which is the best you can do for any of these path searches, but it found really bad paths, so we didn't like it. Breadth-first search basically uses this visited flag, so we'll only ever look at a node once. The first time it reaches a node, it marks it as visited. It takes all the nodes that it can reach through a single edge, through a single street segment, and puts them in the wavefront. So we have this test, right? When we pull a node out of the wavefront, we check, have we visited it before, and if we have, we don't do anything. So what this test means is that we'll only look at a node once. Because once we visit it once, we mark this flag, we'll never look at it again. So we know that while we have a big while loop, we know that with breadth-first search, it will execute a maximum of n times, where that's the number of intersection or nodes. And if we look inside of this loop, we'll also find that all of the work inside of here is just if statements and a loop that goes over all of the outgoing edges. But we already know that there can't be very many outgoing edges from a node in a street graph. The average is about 4. So the work in the loop is actually constant time. It's order 1. So breadth-first search is an order n algorithm, just like depth-first search. And I know roughly what the constant is. So for cities that have 100,000 intersections, this is going to run in less than 1 second. So it'll be pretty fast. But it's not going to get the best or shortest path. So for this milestone, it's not good enough. Now we made a little tweak to it. The little tweak was to not use a visited flag and instead use this slightly different condition. Have I found a better path to this node than I've ever found before? If you do that, I could now look at the same node multiple times, right? I could find it with one path, then I could later find it with a different path, and I could take all the nodes it can reach, put them back in the wavefront. So it's more difficult to bound the runtime of this algorithm, but it can be quite a bit slower. Okay, and I'll demo this towards the end of the class. So this re-expansion was good, and then it got us to better travel paths, but it was bad, and it actually can cost us a lot more CPU time. So we kind of would prefer to look at a node, not very many times. Ideally, we just look at it once, which is what we did here with this visited flag, but that cost us quality. So could we make this algorithm faster by limiting re-expansion? And maybe to give you an idea of that, I'm just going to visualize this on a Toronto map. Okay, so let's say I'm going from this node and trying to find that node. So breadth first search, we go out in these waves, okay? So we start at the source and we look at every node that can be reached in basically one hop. We put those in our wavefront. And then we start pulling those off our wavefront. So we look at and we take all the nodes they can reach. So every node that we can reach in 2 hops are now in our wavefront. And so on, right? Nodes that we can reach in 3 hops, nodes we can reach in 4 hops. We're almost at the destination. But let's say that there were some short streets, back near this destination, but they were really direct. Turns out that they were a little bit faster than some long street that we took. So we find that there's a node in here that we found a path using 4 hops of little streets that is actually shorter than the path we found to it using maybe 1 or 2 hops before. Okay, so because we said if we find a better path to a node, we're going to update its best travel time, and we're going to say, let's look at everything it can reach, and we'll put them into the wavefront. What this basically turns into is a whole bunch of new work, right? It's not just that we look at this node again, we take all of the nodes that it can reach, and we now likely have better travel times for them. So when we pull them off the wavefront, we say, oh, these are all better too. So we have to look at what they can reach, put them in the wavefront. So we wind up with a whole bunch of extra work. And we eventually find the destination, and we backtrack and we get this path. But basically this kind of repeatedly looking at a node and then what it can reach multiple times can really slow our algorithm down. Does everybody kind of have that concept? Okay, seems like you're with me. Okay, so I'm just showing you a piece of the code here again of this breadth first search with re-expansion, so kind of an enhanced breadth first search. And we're right now using a wavefront that is called a FIFO queue, first in, first out. Okay, so I put things into the back of the queue when I find new nodes to put in, right? That's here. I put them in the back. And when I need to take something out of the wavefront to say, okay, let's look at this node, see if we found a better path to it, I take them out of the front. Okay, so that's a queue. Is there a better way that we could do this? It doesn't change very much code, so that we're going to get less of this re-expansion. Okay, finding a node multiple times, and each time we find it, we're finding a better path, which makes us put all of its neighbors back in the wavefront, makes us waste lots of time. So there is a way to do this better, okay, and it's not a big change. So yeah, let's see if anyone has a shot at this. So basically this FIFO queue is what's causing me trouble. Okay, can I do something a little more intelligent, do you think? Let's say this is my queue. So I put in node 78, and it's got a travel time of 20 seconds. So with breadth first search, that's the next node that I'm bringing out of the wavefront. It's the next one I'm going to look at. But I actually know that there's a couple other nodes in here, node 2 and node 39, and they have different travel times. Okay, so node 2 I got to with 5 seconds, node 39 with 12 seconds. So can I do something smarter than just taking the item at the front of the queue, which is what breadth first search does. So what do you think? Well, what's more? Yeah, so I guess I've given you a bunch of hints. Any idea what I could do instead of just taking the item at the front of the queue? I could take the item at the back of the queue, okay? But it's probably not going to be any better. So any ideas of what can I do to sort of limit, I'm trying to reduce the probability or perhaps even completely eliminate this re-expansion. So let's see, what table number are you guys at? H13? You're so far back I can't even see your table number. So, but now you're on the air, speak loudly.
Use a priority queue.
Use a priority queue. So that's a good answer. What does it do? Tell me what that would do.
So like you can, if you use like a min heap implementation of it, then it would have like the lowest time at the top of the queue. And so when we pop, then like we have the lowest time spent when we get rid of it.
Yeah, okay, so this is a good idea. So we're gonna break this down into pieces. So, because you said a bunch of things, all of which are good ideas. But you said use a min heap. We're gonna do that, but people probably don't know what that is yet. So the first thing you said is you wanna get the smallest item. And what you mean by smallest item is the smallest travel time. So if I take the smallest travel time out of this, which was 5 seconds, basically it's pretty intuitive. That is going to reduce, and in fact for simple cases, like basically classic pathfinding cases, it would actually completely eliminate re-expansion. You would never find a shorter travel time to a node because you always start, the next thing you take out of your wavefront, your to-do list, is always the thing with the smallest travel time. So by doing that, if there's the shorter path to a node, you will find it first, okay? So this is a more organized way to proceed. So we want to take the smallest item out of our wavefront, like not smallest node, smallest travel time. And doing that is actually going to, if we didn't have turn penalties, we put turn penalties in this to make it a bit more challenging, but if we didn't have turn penalties, it's actually completely eliminate re-expansion. With turn penalties, we could still get a bit. So if we do this, let's see what happens. Okay, so I'm just gonna walk through our algorithm again, and we're gonna take the smallest entry in the wavefront this time instead of the first one. So we start again at the source. We put the source into the wavefront, and I'm showing here not just the node number, but also the travel time, because that's important now. Okay, so node 0 goes in. It's not our destination. So we look at what it can reach. It can reach 2 nodes, 1 and 2. It can reach 1 with 15 seconds, and it can reach node 2 with 5 seconds. So that's what I've got in my wavefront. And I've got that big while loop. So while loop goes back, we used to take the first item, right? That's what breadth first search does, but now we're gonna take the smallest. So we're gonna take this item. So we look through, we find the smallest travel time is 5 seconds, we take it. Okay, so we go down here, we record that we found the best path we've ever found to node B is 5 seconds, and we reached it, or sorry, the node 2 is 5 seconds, and we reached it through this edge B. We're not done, okay, we're not at our destination, so we basically get rid of that element from our wavefront, but we look at what we can reach, and we can reach node 1. So we put node 1 in the wavefront, and the time to reach node 1 is just 5 seconds so far, plus there's 5 seconds on this edge. That's the travel time of this street segment. And for now, I'm just ignoring turn penalties. But if we had turn penalties, we'd also add it in if it was appropriate. Okay, so that goes into our wavefront. That's the smallest item now, 10 seconds, so I take it off. So I go straight there. I update my travel time to say, okay, I've reached this node with 10 seconds. I got here through edge C. And I keep going. Okay, I'm not at my destination, so I look at what I can reach. I can reach node 3, so we'll put that in the wavefront. Okay, now my smallest item in the wavefront is node 1 with a travel time of 15 seconds. So I'll take that out, but it fails my test, right? My test is that the shortest travel time I've ever seen to this node? And it isn't, right? This node 1 already has a travel time of 10 seconds, so I just throw it away. I don't do anything with that wavefront element. Now I look at node 3, it's not my destination. I look at what it can reach node 4, so I put that in my wavefront, and now when I pull that one off, it is my destination, and I'm done. Okay, and as soon as I reach my destination, I am done. I don't have to keep going. Okay, and if we look at, we invoke our backtrace algorithm that now traces back through these edges. It's going to reconstruct this path, which is actually the shortest path. Okay, so our algorithm now still finds the shortest path, but we did less work. Because we looked at the nodes in a smarter order, we didn't actually have to do any of this re-expansion, where we look at a node, put all of its neighbors onto the wavefront multiple times. Okay, so as I said, without turn penalties, this actually won't do any re-expansion. With turn penalties, it could do a little bit. And this algorithm is important enough that it's given a name. Well, it's named after its inventor, Dijkstra. Okay, so this is a very famous shortest path algorithm. It's the building, not only important in its own right, it's the building block for a lot of other algorithms. It's a very small code change versus breadth-first search. Right, the only code change is that instead of taking the first item in the wavefront, you take the item with the smallest travel time in the wavefront. That's it. So all of what you learned about coding breadth-first search is still very important, because Dijkstra is just an enhancement on breadth-first search. Okay, so let's go. There were some other comments that ece297 made. And let's kind of keep going with how we do this well. Actually, I guess let me ask you first, do you guys understand how this algorithm works? Do you have the basics of how Dijkstra's algorithm functions? Okay, so I'm thinking that sounds good. Okay, so far we've been building our wavefront as a linked list, okay, which can build a queue pretty well, right? We can put things at the end, at the back, and we can take things from the front. But let's think about, is that efficient? It was efficient for breadth-first search. Breadth-first search, we actually were always putting things at the back, pushing them into the wavefront, and we're always popping them out of the front of the list. So it was fine for breadth-first search. But it's maybe not the best, well, it isn't the best, once we switch to Dijkstra's algorithm. So if I have this wavefront, a linked list, and I need to find the smallest item in it, what's the computational complexity of that? So see if anybody remembers this. So I got a linked list, I want to find the smallest item in the linked list. So ece297, what do you think the complexity of that is?
Probably ON.
Yeah, it's order n, right? Linked list, there's no way to find the smallest item except to look through the whole list. So insertion is good, right? Putting things at the back of the linked list is fine, it's order 1, so that's fast. But finding the smallest is very slow. We've got to scan the whole list. So it's order n. I'm not going to call it n. The reason is we've been using n to refer to the number of nodes in the graph. So let's make a new constant. We'll call it m. M is the number of things in the wavefront, okay? So in the worst case, you might have every single node in your graph is in the wavefront, but that's unusual. I showed you those kind of circles. That's the way usually searching a street graph goes. So usually it's more like square root of n. It's kind of like the perimeter of a circle in your graph. But that's still a pretty big number, okay? So, yeah, so this could be order n if we had a graph where we managed to put everything in the wavefront at once. That's unlikely, but order square root of n, because we managed to put, you know, kind of the perimeter of a circle in my graph on the wavefront, is very common. So, yeah, is there anything, well, we actually already heard this. So actually, ece297, do you have a comment or question?
Yeah, about a better data structure.
What do you think?
What about a unordered list or an unordered map?
An unordered, okay, so you want to use an unordered list we kind of already have, that's a linked list, but an unordered map is a hash table, right? Yeah. So, okay, so we want the smallest item. Can an unordered map give us the smallest item in it?
Probably, I don't have the like functions of the STL container.
Just think about the data structure. So an unordered map's really good for lookups because we do this hash function and we can find, so we have a key and we give the key and we can quite quickly in order one find something with that key because of this hash function letting us look up quickly. But an unordered map is not sorted. An unordered map has no way to find the smallest item except to go through the whole map. So an unordered map for this purpose is no better than a linked list. In fact, it might be a little, well, it's hard to say if it's worse or not, but it's also order n. So an unordered map won't work too well. We heard you, yeah, so any other ideas? We actually heard one already from H13, but I'm going to see if anybody else heard that. So let's see, D04, I think you buzzed in. Where are you guys? Yeah, what do you think?
We were thinking a set or a binary search tree.
So you're thinking a binary search tree, is that right? I didn't hear what the first thing you said was.
A set.
What is it called?
Set?
Oh, a set, yeah, okay, yeah. Set is a variation of a binary search tree. So yeah, binary search tree is a good choice. And of the data structures that you were taught in 244, it's the best choice, okay? So yeah, if we use a binary tree, it's naturally ordered. And a wavefront, we're gonna stick stuff in it a lot. So we actually care about how long it takes to insert things, what's called a push operation. And we also care a lot about how long it takes us to take the smallest item out. A binary search tree, these are both logarithmic in the number of nodes in the tree. So we're calling the number of items in the wavefronts m, so basically it's log m to insert things and it's log m to remove the smallest item. So a binary search tree is a good choice. Where the linked list insertion was really fast, but finding the smallest was really slow. And the sum of them is much worse than what we get for a binary search tree. Okay, so let's put this into an overall complexity. So if we use a linked list, our work to take an item out of the wavefront and process it is between n to the 0.5 and n, or an order n, depending on how much stuff is in our wavefront. For a binary search tree, it's order logarithm, number of things in the wavefront. And we know we can't have more things in the wavefront than are in the whole graph, so that's for sure less than or equal to log n. If I basically write some code to try this, these turn into huge numbers. So depending on how big the city is, your path search with a linked list and Dijkstra's algorithm will take you from 3.2 seconds to 1,000 seconds, so based on the numbers that I got when I coded this. With a binary tree, it'll be less than a second. So again, this shows complexity matters, right? Using a data structure with the wrong complexity can be catastrophic. So we do not want to use a linked list for this. It's a really bad choice. A binary search tree is a pretty good choice. So it's going to make Dijkstra's algorithm quite fast. Basically because the overall complexity will be order n log n, right? We could look at every single node in the graph, and for every single node in the graph, we could put it in the wavefront, we could take it out of the wavefront. Well, that's log n work times n things. Whereas with a linked list, most likely our wavefront had about square root of the nodes in the graph in it. So we do, for n nodes, we do square root of n work. That's order n to the 1.5. Those might look somewhat close, but you wind up with these big differences in CPU time depending on how big n is. So we really don't want to use a linked list here. Okay, so everybody with me so far? So binary search tree, a much, much better choice for this the wavefront than linked list. Okay, is there anything faster than a binary tree? And I'm pretty sure H13 already knows about this. So if nobody else has an idea, I'm going to call on them again. Maybe I'll call on H13 again. So you already told me this. So you know something better than binary search tree. Do you want to describe what it is?
So if you use a min heap, maybe an array representation of it. A min heap is so that like at each node, its children node have a higher priority. So when you're removing, it's O of 1 time because you just pop the top of the list. And when you insert, it takes O of log n, because it needs to traverse down the height of the tree-like structure.
Yeah, so that's a good answer. So I'm just going to repeat that. So you're saying use something called a min heap. I'm going to show you what that is. A min heap it's very closely related to a binary search tree. It partially sorts its data rather than fully sorting it. A binary search tree is completely sorted, right? At every node, the left child is less than the right child. So a node is greater than its left child and less than its right child in a binary search tree. A heap is somewhat ordered, but less, and it makes it somewhat faster than a binary search tree when you don't need total ordering. Okay, so let me draw it. So a heap is not faster in its overall complexity, like its asymptotic complexity. So insertion is still order log n, and removal of the smallest element is also order log n. Well, those are the same as a binary search tree, right? So it doesn't change the big O notation of what you're doing, but it is faster by a constant. Constant is probably around 3x, so it's noticeable, it's worth getting. Okay, so how does it work? So basically, a heap has a weaker sorting property than a binary search tree, and that's why updates are a little bit less work, and that's why it's faster by a constant factor. So I'm doing what's called a min heap. A min heap is basically, it's a partially sorted binary tree, and the smallest item is always at the top, at the root. Okay. And that's what we want, because we want to be able to get the smallest item quickly. We don't really care about the biggest item. We want the smallest travel time all the time. So I'm showing you here a bunch of travel times. And this would be a valid heap for these travel times. So each of these things would represent a node in our wavefront. So at the top, I've got a travel time of 3. That's the smallest one. And the property a heap must meet is that a node, for a min heap, a node must have a smaller value, travel time, than either of its children. So notice this node, its 2 children have travel times that are both bigger. This node has travel times of its children are also bigger. This node, its travel time of its children is also bigger. So every node meets that property, but notice there's no ordering between children. So this is not a binary search tree, because in a binary search tree, the left child, well, this would be a binary search tree that's kind of a greater binary search tree. So the left child would have to be more than this node. Well, let's see, let's take this one. The left child here, with the sorting function I'm using, would have to be more than this node, and it is, but this would have to be less. Okay? So between these children, there's no ordering relation, right? In this one, the right child is less than the left. In this one, the right child is more than the left. Okay, so smallest item's always at the root, and there's no ordering between the nodes at a single level of the heap, but there is this ordering between levels, okay? The parent always has a lower travel time than the children. Does that make sense? It's effectively a partially sorted binary tree. Okay, so you don't need to implement a binary heap from scratch if you don't want to, but it's useful to know how they work. So if I want to remove the smallest item from a binary search tree, and that's what I'm doing whenever I'm taking something out of my wavefront. What I do is I know exactly where it is. It's at the root of the tree. I take that item, I remove it. Okay, I'll go do some processing with it. But now I've got to fix my heap. This is not a heap anymore because there's an item missing. The way I fix it is I take an item from the bottom, which will be large, and I move it into that empty spot. Okay, and this is not a heap anymore because this node is actually bigger than its children. So we can't do that. So what we do is we do a fix-up phase now. So we compare this node with travel time 50 to its 2 children, and we'll swap it with the smaller one if we have to. Okay, so we look at these 2 children, this one's the smaller one, and we'll say, is it smaller than my value? It is, so I'm going to swap with it. Okay? And then I repeat that. Okay, so I've moved node 50 over here, but maybe it's still not in the right spot. So I'm going to compare it to its 2 children again. Okay, I'm going to see which of those two children is smaller. It's 35. That is smaller than 50, so I'm going to swap again. And I do that for every level of the tree. There are only log n levels, right? It's a binary tree. So I only did this comparison and swap at most log n times. I'm not going to show you what happens when you insert an element, but it's similar. You basically would add it into the bottom here, and then you do these swaps to fix up the heap again. But again, you do log n of them, you just compare with its parents. So that's why it's order log n for both insert a new element and remove the smallest element. You don't have to code this from scratch. In the standard template library, there is a heap, so you can use it. You can also use something called a priority queue. A priority queue is also a heap. It's just basically a little bit of wrapper around a heap, but inside of it, it's a heap. What a priority queue is you basically can push items into it, and you can pop off the smallest item, which is exactly what you want to do in Dijkstra's algorithm. So you can do that by directly instantiating a heap in STL, or you can just ask for a priority queue in STL, or you can write it by hand. But writing it by hand is more work. Any questions on that, on how any of this works? Okay, so in that case, let me do a quick demo. Okay, so let's start off with depth first search. So I've got a little button over here that can choose what kind of search algorithm I'm using, and I just click on a destination and it's going to plot a path to it. Okay, so I'm not really slowing it down as much now. I'm slowing the graphics down a little bit. But remember, depth first search, it's fast, but it's kind of chaotic, right? It's exploring all over the whole graph. It finds these really long travel paths. So like, yeah, that is a driving route inside Toronto that is 8,600 minutes. So that's a really bad driving route. So I'm going to switch this now to breadth first. Actually, before I do that, I'm going to see where let me do one last search down to here. Oh, that was Dijkstra. Okay, so I did it in the wrong order. Let's do this again. Okay, so I'm going to do a breadth first search. And breadth first search found a good travel path. So that's 18 minutes to go a moderate distance. Let's do it again. Okay, so it found that travel path is 17 minutes to go a moderate distance, so it's getting good paths. The version of breadth first search I'm showing you here is kind of like the enhanced breadth first search. It's not the classic one, it's the one that does the re-expansion. So it does get the shortest path. Now, the problem with it is as I get further away, it gets slower. So I go a little further away. Yeah, I have to be careful how far away I go. You see it starts slowing down. And it's slowing down because it's finding better paths to some of the nodes it already went to, and kind of getting slower and slower as it goes farther. So it doesn't scale very well. Okay, but it is finding good paths. Okay, so if I change how I sort the wavefront, well, I do sort it with a priority queue. I take the smallest item out. I get Dijkstra's algorithm, and Dijkstra's algorithm is very fast. So you can see Dijkstra's algorithm, it doesn't do any backtracking. When it finds a node and pulls it off, that's basically the best path to it. Again, with turn penalties, maybe it's not quite the best path, but it'll be close. So there's minimal re-expansion, and it's much faster. So it explores in a pretty orderly fashion, and it's finding good travel paths. That went a good chunk of the way across Toronto, and it took 29 minutes. Okay, so it works much better. So Dijkstra is like for milestone 3, Dijkstra is the first kind of good algorithm, okay? I'm going to show you an enhancement to Dijkstra that can be even better, but it's not much more code. And Dijkstra is very close to breadth first search, but you want to take what we've talked about in lecture. Do not implement depth first search. It's a bad algorithm for this purpose. Implement Dijkstra's algorithm. It's a good algorithm. Okay, can we do even better than Dijkstra? So Dijkstra is pretty smart. It expands out in waves. It avoids redoing work because of the fact that it's sorting the wavefront, while it's always taking the smallest item out of the wavefront. So it's pretty good. But if you look at this, you can see, well, I was going from a certain intersection kind of northwest. And Dijkstra's algorithm will explore in the northwest direction, but it actually explores just as much in the southeast direction, right? So, and you think, well, if you were doing this by hand with a paper map, you probably wouldn't go in circles like this looking for travel paths. You'd be like, well, maybe I should go towards the actual destination. That seems more likely to lead me to a good travel path. So, there's a fair amount of extra work that happened here where you go, what were you doing? You were expanding outwards in the wrong direction, and it's pretty unlikely that you're going to find a good solution out there. So we can add in additional smarts to the algorithm that can make it faster by being a little more targeted in how it explores things. Okay, so any ideas? How can we make this better? So I told you if I was doing this with a paper map, I'd tend to explore in the direction of the destination, right? That's the basic idea. So how would you do that? I think H13, I'm going to go to you again. Well, maybe you're still on, actually. Sorry, that might be from last time. Okay, so anybody have an idea of how can we make this faster? So B10.
Can we find the angle between the intersection like out of a range?
Okay. Okay, so you're saying find an angle. Which direction am I going? And maybe only explore, I think what you're saying is only explore nodes that are kind of maybe in a certain range of that angle. Does that make sense? So going in the exact angle might be too limiting, but you're going to say, okay, if this is 45 degrees, like straight, if this is directly northwest, maybe you'll look north, you look west, and everything in between. But you won't look like southeast and so on. Okay, so that's reasonable. And basically you would code that when you are looking at a node and considering putting it in the wavefront, or you can also code it as when you take something out of the wavefront, you would check, well, what direction am I going? And if it doesn't meet this criterion, you would just say throw it away. Does that make sense? Okay, so that's a good idea. And so well, I had a similar idea. It's not exactly the same as yours, of what if I basically said, if only look at a node if it gets you closer to the destination. So I could look at what is my distance to the destination of the node I'm considering putting into the wavefront, and compare that to the distance to the destination of its predecessor, the node that got me here, and I'll only put it in if it actually is closer, so it's going in the right direction. But I could also do exactly what you said. I could recode this as basically, only go there, or basically angle in proper range. That is a different way of doing this, but it's kind of a similar idea. Throw away things that are going in the wrong direction. Okay, so you could do that, but it's a little dangerous. The reason it's dangerous is you have things like this. I've got an intersection here and I want to get across the 401. And there is no direct path to go across the 401. Don't try that, right? So if you build a map that just says go straight across all the lanes of the 401, this would not be, you would get a very bad grade, right? If you survive testing of your map. So what you'd have to do is you have to go out of your way some. You find a road that crosses the 401, you go across, you come back. It turns out there's actually no road right here, so we have to go a little further still, but we can get there. But there's some detouring. So you're gonna find portions of a city that look like this, where if you have sort of aggressive pruning conditions like this, where you say, well, you can never go further away from your destination. Well, I did that. I actually moved further away from it. So my pruning condition would forbid this. I wouldn't look at that. I'd throw it away. The pruning condition that B10 proposed also would throw this away, because this is, you're basically saying have a range of angles and only look in that range. Well, I'm outside that range. So these are reasonable ideas, but this is a bit too aggressive. There'll be places where they result in no solution. There'll be other places where they result in some solution, but it's not the fastest. So we have to be a little less aggressive than this. And I think I'm basically out of time, so I think I'll leave it for there. We'll talk about it on Thursday. I guess the hint